Hey everybody, in this video we're going to explore some very basic ways of defining an injective function from one set to another. Here we've been given three different sets. We have an S, a T, and a U. So let's see, S has four elements, T has four elements, and U has four elements. And that has three elements, excuse me, and that might come into play later on, we'll see. So the first question is asking us to define two different injective functions from S to T. So it would probably be helpful to remember what injective means. So you remember when we talked about functions, I call them a domain condition, right? To be a function is a domain condition. The idea being with a function that say went from some S to some T, to be a function, you need to check each dot and make sure that there's at least one line coming out of it, right? And when I say at least, of course, why do you need at least? Well, everything in here should be in the domain, right? S is the domain. But you also need to make sure that there's at most one line coming out. One of our definitions of a function is that you cannot have two different lines coming out of the same dot. Okay, this is like the circle example, right? Probably from high school where you showed it fails the vertical line test. Okay, you cannot have two lines going out. Of course, all these lines need to end up in T. That is true, right? That's something useful about the codomain there, right? But everything has to end up in there. But you cannot have two lines coming out of one. So this is what it means to be a function. Injective is a codomain condition. So you're looking at the codomain, and you want to make sure that there is at most one line going into each dot. Now you notice I didn't have a line going into the bottom dot. That's okay. Injectivity doesn't require you to have a line going into each dot. It just says you can't have a second line going into the same dot. Now, another name you often hear for injective functions is one-to-one. I think that's honestly a mistake. It causes all sorts of confusion. Students hear one-to-one and they think, oh, one dot on the left has to go to one dot on the right. Well, that's the definition of a function, right? That's a domain condition. If anything, it should be one from one, right? One dot on the left or on the right should come from one dot on the left. Right? We're not allowed to have the second line going in. In any case, let's get back to the problem. We wanted to build an injective function from this given S to this given T. In fact, we want two of them. So let's draw a couple of examples. So we'll write down the function or the sets S and T. So we have 1, 2, 3, and 4, and we have A, B, C, and D. Now, we just said the rule for having an injective function was that you cannot have more than one line going into each dot on the right. So let's take this A, and we got to have a line coming out of it. Where should it go? Well, I mean, I don't know. How about 1, right? So that would mean that the function would send 1 to A. And how about B? Well, we got to go to somewhere not 1, right? So, okay, there we go. 2 goes to B, and how about 3 goes to C, and 4 goes to T. Why not? So there is a function, and it's injective because from each point in the codomain, there's only one arrow going into it. All right, let's try another one. S and T, and we have number 1, 2, 3, and 4, then the letters A, B, C, and D. All right, well, again, something needs to go into A or not. What if nothing went into A? How about we try that, right? Let's try having nothing go into A. But at least one thing should go into B, right? So maybe 1 goes into B, and then 2 can go into C, and 3, say, can go into D. And now we have a little problem. What's the problem, right? Well, it's not that we have lost injectivity, right? We don't have two arrows going into the same thing. But we don't even have a function because we need every element in the domain to go somewhere. So 4's got to go somewhere. Oh, thankfully, we have A left over. So why not? We'll have 4 go to A, and maybe this function could be called G. All right, so there we go. So remember, we start from the right-hand side when we're trying to build injective functions and work our way backward. All right, what's the second one? We want to define a function from S to T That is not injective. Okay, well, since we're trying to show something is not injective, why don't we start from the right and just make it so that we lose injectivity? So we'll draw our picture. We have an S and we have a T. Here's our 1, 2, 3, and 4. We have an A, B, C, and D. And since we're trying to break injectivity, and we know you break it by having two lines going into one point, well, why don't we put two lines, say, going into A? We'll have the 1 go into A, and well, why not the 2 going into A? Okay, well, it's not a function yet because we haven't said what happens to 3 and 4, but well, okay, we'll just make it nice and simple. 3 goes to C and 4 goes to D. Why not? Where could we have sent 3 and 4 somewhere else? Sure, we could have sent everything to A. Right? As long as we have at least two arrows going into one, and we have one arrow coming out of each on the left, we're going to have a function, and it will be not an injective function. Okay, last problem, and this actually uses a set we haven't talked about yet, which is why there's no injective function from S to U. So let's draw S and U, and we'll see we've actually answered this question already, but when we were talking about S to T. So we have 1, 2, 3, and 4. And then U consists of a circle, an asterisk, and, well, you guys haven't seen this probably much in math before, but this is usually called a tensor product sign. In LaTeX, by the way, O times. That's kind of nice. Okay, so we want to build, let's say we're trying to show there is no injective function, but let's say we were trying to build an injective function. How would we do it? Well, we know there needs to be one line coming out of each of these. Can't have two. Well, there's only 3 lines here. This dot, where does this come from? Well, maybe it came from 1, and maybe this one came from 2, and maybe this one came from 3. But now there's nowhere for 4 to go. Okay, so this is really an application of the pigeonhole principle. When you have 3 mailboxes and 4 letters, and every letter has to go into a mailbox, you're going to have to double up at least once. Okay, so the sort of the clever answer to this question is it's prohibited by the pigeonhole principle. Okay, yeah, and it's basically what's the problem is you have fewer objects on the right than you have on the left. So we could actually write down a more general result here. So if S and U are, let's say, finite sets, such that the cardinality of S, so the number of elements in S, is strictly greater than the number of elements in U, then there is no injective function from S to U. Okay, and you can see it by just, well, you take every element in U, map it backward, you get one arrow coming out. It's not enough to fill up all of S. And so you won't even get a function in that way.